Hello, everyone. Today we're doing Chaotic Dynamical Systems Abstract Art by me, Ilyas Rehman, Manvi Sharma, and Veer Banwait.
Hello everyone, I'm Manvi. So before we begin with the actual project, we just wanted to give a brief overview on the origins of chaos theory. So the picture that you see is of Edward Lorenz, a student from MIT, and he's known as the official discoverer of chaos theory. So from a very young age, Lorenz was interested in weather forecasting and weather patterns, which is why he became a meteorologist. He worked with a system of equations to predict the weather at a specific location months apart. He thought, along with many of the scientists at that time period, that the weather or the changes in the beginning of a calculation would lead to small changes in the outcome. So he computed the equations and thought that given a starting point, the weather would result exactly the same each time, and that slight variations in the beginning would lead to the weather being slightly different. For example, a small variation could be like a puff of wind, which is unlikely to change the large-scale features of the weather. However, the initially thought to be small changes later proved on to be catastrophic. So we've all heard of the famous quote, "Does the flap of a butterfly's wings in Brazil set off a tornado in Texas?" This is called the butterfly effect, which was derived from Lorenz's experiment. This ties in directly with our main topic, which is chaotic dynamical systems. So the textbook definition is given up on the board, but in simple terms, it means that tiny changes in the initial conditions can lead to vast outcomes over a period of time. So some examples of these systems could be population growth, a swinging pendulum, or even motions of celestial bodies. So if I were to ask all of you to characterize chaos in one word, most of us would probably say unpredictable. Chaos is omnipresent in our world, but chaos in mathematics has given rise to the term chaotic dynamical systems. These systems exhibit chaotic behavior and have sensitive dependence on initial conditions. These systems also have strange attractors, which have chaotic motion and aperiodic orbits. So many versions of these attractors exist, such as the Rossler attractor or the Lorentz attractor, and these can be shown in many different ways, such as bifurcation diagrams and cobweb plots. So cobweb plots show attracting and repelling behavior, whereas bifurcation diagrams show period doubling and tripling. This usually occurs when a system undergoes a drastic and chaotic change. All right, so the unique property of abstract art is that the meaning of it lies solely in the hands of the beholder. Abstract art avoids reality, but uses shapes, forms, colors, and textures to achieve its effect. Chaotic dynamical systems exhibit this behavior using mathematics, nonetheless inspiring awe and wonder at the sight of one. So the story, if there ever is one, behind an abstract art piece is only known to the artist. But when observing a chaotic system, you know that it is created with mathematics, though some systems that we've seen do rise from naturally occurring phenomenons. Thank you. I'll leave it to Veer now.
Hello, Veer. So if you look on your left here, this graph on your left, it looks quite odd and not very interesting. In fact, it looks quite random. The graph here is created by generating angles through iterating a chaotic function. The chaotic function is shown at the bottom over here, t times x times 1 minus x, where t is a constant and equals 3.9. T equals 3.9 is where most of the chaos actually occurs. If we change that to, say, 4 or change that to 3.8, then it causes the outputs to become more regular. The graph then draws a line that's 1 unit long from the last endpoint to the new one in the direction of the angle generated. This graph right here is taken only after 10 iterations and is boring because there aren't any discernible patterns or attributes. But as we move along to more and more iterations, you can see on your right here that there's a graph after 1,000 iterations. The angles clearly favor the right side. They also form large climbs and steep drops. Using these chaotic patterns as a mold, we have used AI to create abstract art. The following sets of slides provides an in-depth overview of the process of creating two more complex and intricate art pieces. For the next few pieces, we utilized the programming language C++ to graph our chaotic dynamical systems and animate them using a time variable, which stood in place as a constant variable usually used in dynamical systems. Points were created and initialized to the time variable for the first few steps. So say t, or time, equals 2, the x would be 2, and the y would also be 2. And then the points would be, each step through the time variable would update the x and y slopes dependent on the time, the x value, and the y value, and then it would generate the new point, causing the points to move in chaotic directions over the time. This would allow the system to iterate through its bifurcations and create a moving picture. Then we applied artificial intelligence models to static frames that we chose ourselves to create the abstract art. Our chaotic dynamical system animations were already art in itself. But to create art in a more traditional way, say a painting or a picture, something like that, we utilized AI. Okay. Firstly, we set up the chaotic equations for each of the derivatives and then use the code to animate it. See here, you can see that the slope is determined by the x, y, and t for each of the x and y points. So if I click here, you can see that there's an animation. I'm not sure if you can see it. Okay, sorry about that. So you can see the points get generated and then start moving around. And if you wait a little bit, they start to come together. And you can see that the t, or the time step variable, is on the right side, the top right side. You can see it moving. The points come around, and they come together, and the derivatives, a thicker line means that the derivatives of multiple points are actually coming very close together. So they're attracting, and you can see now it's getting really thick and really close together. So that is, okay. Our second step was to take a snapshot. Here was one frame that we thought looked very interesting. And as you can see, the thick lines indicate that the derivatives for multiple points in different starting locations actually ended up quite close together after going through the time. And then they created patterns and attractors, as we can see in the next slide. Here we outlined the general shape, which is in red, the average path and flow, which is in blue, and the strange attractors, that is in green. We then fed the image with the outlines into an AI art generator, and we got the artwork in 2 different styles, while still keeping the attributes that were in our original chaotic graph. The top here is a modern style artwork, while the bottom is a Picasso style artwork. And here are our final results. This is the finished art piece. And now I'll hand it off to Ilyas.
Hello. So today, this time, we're going to go into our second art piece right here. So see from these 2 equations, they look pretty simple when looking at dynamical systems. And I'll show you what it looks like. It looks like something really crazy. Let me show you. All right. So let me move that out of the way. So it starts instantly, and we started at around time -1. So it forms this really weird shape, and you can see the gaps where the derivative isn't the strongest is usually a strange attractor. And when we get into analyzing it, this has an odd amount of strange attractors. And over enough time intervals, it starts to become smaller and get an even amount of strange attractors. So through these animations, you can really see what the time variable will do to a chaotic dynamical system when it's a constant. And I think that's enough of that. It just stays like that and becomes more solid. So here are the two snapshots we took. One of the odd amount of strange attractors and one about the even strange attractors using the same equation but just different time. Right here, this is where we outlined red, blue, and green. So general outline is usually what the AI takes to make the general format of the art. So if there's a face here, it would generally take that as the model to use for it. Blue is the average flow. So if we have it do paint brushes, stuff like that to make it like more artsy, it usually follows the blue lines. Green lines are the strange attractors and usually the main center of attention for the AI model. And from the top one, you can see there's only 2 in the top, and then it goes into 3, 4, 5, 6, 7 in odd amount. The bottom one, you can see has way more strange attractors. It becomes way more condensed, but also has more strange attractors, which it orbits around. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So a lot more came, but an even amount too. So we applied 2 models to this one. One is a more modern art, and one is a more Picasso feel. So using that and feeding the analyzed models that we did, we got these 2 artworks. So the Picasso one uses general style of shapes and abstract art, but the top ones are the abstract art and use a black and white contrast. So these, we made plenty of them. We're exploring a bunch of dynamical systems and trying to make them into feasible art. So as you can see, all of these look like art pieces if you didn't know there were math behind them. But if I go to the next one, you can see all of them are derived from these. Conclusion. The pattern-like mathematical meaning behind an abstract piece of art adds a lot of value to it. But chaotic dynamical systems emulate the natural style people have when creating art. AI further pushes the idea by applying it to the systems. Nonetheless, chaotic theory reveals the intricate and often surprising nature of the world around us. As we've seen before, totally random behaviors from simple systems can often lead to appealing pieces of art, showing that there's beauty in chaos. Here's our sources, and at the end of our presentation.